So we will start with Florent Krzakala from ENS and Sorbonne, who's going to tell us about Rademacher complexity and spin glasses, a hidden link between the replica and statistical theories of learning.
All right, thank you. So the talk is about the Rademacher complexity and spin glasses. And really it's about a link between two different kind of approaches, or should I say communities. On one hand, statistical theory and statistical theoreticians, and on the other one, physicists who used the replica method trying to say something about theoretical machine learning and statistics. And this is joint work with my students, Alia Abara, Benjamin Aubin, and my collaborator, Lanka Deborah. All right, let's go. So first, let me briefly go with brief recap of statistical learning. So consider, for the sake of simplicity, a supervised binary classification problem. You have a data set, M example, you have label, Y, which are plus or minus 1, you have a vector X, and you have M such pairs. And what you are trying to do typically is to fit the problem with a function that belongs to a function class F. And one of the most important theorems that we have in statistical learning is uniform convergence. And there are many forms of these. One of them can be expressed as follows. So with high probability, the generalization error minus the training error, the difference between these two is bounded by this object called the Rademacher complexity plus a little correction. The Rademacher complexity is a fairly complicated object. I will come back to it later on. But the classical result is that the Rademacher complexity is itself bounded by the VC dimension, more precisely by a constant times the square root of the VC dimension divided by the number of samples. And now, of course, if M is large enough and the VC dimension finite, well, we see that the difference between generalization and training error goes to 0. And this is what we use in statistics. And essentially, this is a starting point of many books on statistical learning. All right, now let me switch gear and move to the physics community. So physicists likes model, and when they were trying to look into what they could do on such problem in stat and machine learning, that was, let's say, in the late 80s, they were, instead of trying to understand how to make uniform bounds and worst case analysis, to try to see what is going on when you study model of data. And in particular, they were looking to the setting called the teacher-student framework. So in the simplest version, it's kind of a caricature of a problem. Well, you have data, your vectors are all random. So you have m d-dimensional vector, they are all chosen randomly. In fact, you can even make the sample model where all these components are just Gaussian. And the label are given by a function, which is called the teacher. For instance, and again, this is the simplest version, it can be just the sign of the vector times the vector W star, which is hidden. And you can also choose it randomly. And what was typical already in this late 80s paper was to study the high dimensional limit. When m, the number of points, and d, the dimension, goes to infinity, with alpha m divided by d fixed. Now, there are many generalizations to such settings. And in fact, the literature of statistical physics is full of this problem. And these days, in fact, such problems are extremely popular even in statistics and machine learning. All right, let me just present the kind of results that were obtained at the time in the beginning of the 90s. So for instance, for the setting I just described, you can compute the generalization error if you try to apply different fitting procedure. For instance, the black curve here tells you what is the generalization error if you try to use Bayes formula. And this is, of course, the best we can do, even though most of the time it's not computationally feasible. You can also compute what happened if you use empirical risk minimization. There is a nice paper by Hopper in '95 where he computes what happened with the ridge problem without any regularization, so the pseudo-inverse. He obtained what you see here as a red curve, and he saw this behavior that is now very trendy and called double descent, which was already observed in the 90s. He also computed max margin solution. This is a blue curve, and many others. So that was at the early 90s, and it took quite some time for these heuristic results to be turned to rigorous proof. That's just happened, let's say, in the recent few years, and all this now is with control. All right, so this is a recap. Now let's come back to the subject of the talk. How does the uniform Rademacher bound and statistical learning fits in this story? Or if you want, now that we have seen what is going on with some typical data and what happens when you actually feed them, we can ask how good is the Rademacher bound in this particular teacher-student problem? Okay, and that's essentially the kind of question we are trying to answer in our paper. So there are now three take-home messages of main result, if you want. Here is the first one. First of all, the Rademacher complexity, which is a very complicated object, actually, can be computed analytically using this heuristic method called Replica by physicists in these high-dimensional synthetic problems. And it's actually very interesting to observe the serendipity here. Physicists knew nothing in the 80s or in the 90s, for that matter, about Rademacher complexity, so they were not computing it. They were computing something else. So this is a definition of Rademacher complexity. What it means essentially is, well, you take M vector from your ensemble, you pick up a random label, and then you try to pick up which function F in your function class is fitting them the best. Okay, so the Rademacher complexity is telling you how good you are with fitting random labels. And interestingly, physicists were computing the same kind of quantities. They called it the ground state energy of the garnered capacity problem, but it's really the same. And in fact, the formula between one and the other is given here. And you see the ground state is just up to a trivial factor 1 minus the Rademacher complexity. So they were looking to this object already at the time. And the way they were doing it was using this method called the Replica method, which is a heuristic powerful method. So for instance, for our simplest model we have been discussing so far, again, all vectors are d-dimensional random vector. If you try to fit them with a function class, which is the one mentioned here, sine of x times a vector, or if you want the class of all separating hyperplane, well, if you send m and d to infinity with alpha fixed, you have an ugly looking formula, which I'm just showing here. I will certainly not explain it, which is supposedly answering this. I'm saying supposedly because it's a heuristic method. And even though we have obtained a lot of results in the rigorous control of these techniques, especially thanks to the amazing work of Michel Talagrand, we are still far from a full rigorous control, but we are all confident that it works pretty well. Now, instead of looking at the formula, let's see what it actually means. For this problem, the first thing is that the Rademacher complexity has a non-trivial well-defined limit when m and d goes to infinity together with a fixed ratio. This is actually how it looks like. For small alpha, well, alpha is smaller than 2, well, actually, you can always fit perfectly noise. It's a very well famous known result by Cover. Physicists call that the garner capacity. So until alpha equal 2, the Rademacher complexity is 1. After that, well, your function class is not good enough to fit random labels, and it starts to decay below 1, and it decays actually as 1 over square root of alpha. So what you see here is the result of the Replica method, and here in log you see very well this 1 over square root of alpha. All right, so that's the first result. Now let's look at the second result, which is here, which is perhaps not surprising this day, is that the bound given by the Rademacher approach for this very problem is almost entirely vacuous. So here I'm showing again these three curves that I showed you a few minutes ago for the problem where you had the teacher and the student was just a sign with an hidden vector. So the base curve is a black curve. The blue curve is the max margin. In fact, if you use logistic or hinge, you get basically the same kind of result. And only ridge, it's getting bad. But still, Rademacher is very far from all of this. And worse than that, there is nothing wrong being far. It gives a wrong rate. It gives a rate that decay, the generalization gap decay as the inverse of square root of alpha. While what we see in practice, and I was really blown away when I did the simulation, and then we made the computation, is that you just plug scikit-learn and you launch max margin or logistic or hinge, and you actually get essentially the base optimal results and the base rate 1 over alpha. And I think this is a nice, a good illustration of the difference between, what you get when you have uniform convergence and what could happen in reality. And in fact, there was a very nice paper already in the physics community in '93 we showed that the problem is, of course, the requirement of uniform convergence in the Rademacher bound, because it exists some function that gives you a 1 over square root of alpha gap. And if you want to be uniform, of course, you will fill this. And you will miss the fact that the optimal solution goes of 1 over square root of alpha, 1 over alpha. All right, and the last point I wanted to discuss is the fact that even though I presented this result for the simplest problem, with effort and with some work, you can generalize it to more interesting or perhaps more challenging problem. So for instance, if you are using what we call the committee machine, which is a 2-layer network, and your data are still random, but now the teacher is a 2-layer network, and your function class, or the student, to use a statistical physics parlance, is also a 2-layer network. You can repeat most of this computation, even though they get really tricky. And again, you can observe interesting phenomena and clear difference between what happened with worst case uniform bound analysis and in that case, the base optimal result. So briefly, what happens is that the Rademacher bound starts to give you something non-trivial when alpha is larger than order k square root of log k, where k here is the number of neurons in the first layer. Base optimal result, however, start to be extremely good, and again, have a generalization error that they can like the inverse of alpha already when the number of data divided by its dimension is order k. So you see there is a sizable gap that open between the two. And I think this is another interesting illustration of the differences between typical case analysis and some more uniform bound with worst case scenario. All right, I think I'm close to my 12 minutes, so I will conclude. So I presented you what I think was an interesting connection between statistical learning and some work in the Replica literature. In a nutshell, we have this Rademacher complexities. For some very simple model, they can be computed analytically and in the high-dimensional limits, thanks to the Replica method. And there is some interesting question here about how much we can prove things here. It's not trivial, by the way. This will probably be a challenge mathematically. And it allows to illustrate the difference between what we observe with uniform bound and typical, let's say, more favorable typical behavior that we get sometime. And there are many future directions that we could take after this work, and I will let's face for the future, of course. And finally, I want to, again, thank my collaborator on this project, Alia Abara, Benjamin Aubin, and Lankas Deborova. Thank you for your attention.
So Florent has already very interesting discussion going on Slack. Before we get any questions, Florent, do you want to give the executive summary of this?
Yes. Yeah, give me a week. Well, no,
okay,
Jason only pointed out a very nice reference where some more interesting bound might be able to predict the 1 over alpha behavior. So thanks to him, and so we are reading this paper and learn about them. But of course, you know, yeah, there is a lot of room beyond Rademacher bounds.
And so I had a question for you actually that I'll take the opportunity to ask. So on the teacher-student example that you showed, is there any computational gaps where you have you showed us the Bayes and the Rademacher bound, but what can you do computationally?
Question. Very good question. Let me go back to the slide if you don't mind. Do you see them?
Yes,
all right.
Yes, we see them.
I assume your question was not about this, because that was with a convex problem. So
yeah, I mean the other one, yeah.
All right, and here you are perfectly right. Indeed, the Bayes result is very different from what we get computationally. There is indeed a huge gap, and in fact, the best algorithm we know here start to give results which are good when alpha is of order k square. So actually, this problem is extremely hard as far as we know. We don't know any algorithm that is very efficient to solve it.
Interesting. Okay, thank you. And by algorithm, you mean like gradient descent, or what do you mean by
Well,
the algorithm that
good
something
point.
like this?
The one we were able to, okay, so we tried gradient descent, it did not work, but we don't know to analyze it here. Well, we are trying. The one we were able to analyze, obviously, as you might have guessed, is message passing ones. And they need really a huge number of samples to give something better than random. Really case, you need to have alpha larger than k square. So it's really terrible, actually. Algorithmically, this problem seems to be very, very hard.
See, okay, thank you.